This 2 to the power of n minus prime number, the all integers is greater than or equal. Two to the power of n is a minus one or here? Okay, minus one is a prime. For all, okay, prime for all n greater than or equal to 2. Okay. Is it any prove or disprove, right? So there's no condition like any. Let's do induction. Let's do it induction. So if we use the induction, if base case n equal to 1, so 2 to the power of 1 minus 1 is 1. Okay. If let's say one more case and then we move on. 2 to the power of 2 minus 1 is 3. Okay. So if n equal to k, this is 2 to the power of k minus 1, which is a prime. And now n equal to k plus 1. So 2 to the power of k plus 1 minus 1. That is a prime. Why? Because this I can write it as 2 to the power of 2 to the power of k into 2 minus 1. Right? It's k plus 1. And this is equal to, and 2 into 2 to the power of k minus 1. So again, this is going to be a prime when we get multiplied it by, I mean, not the whole, 2 to the power. Now, if I take any number here also, it's going to be a prime. So for example, if I take k equal to any number, because it can be a even also. So if it is k is 4, then 2 into 2 to the power of 4 minus 1. 2 to the power of 4 is 16. 16 times 2 is 32. 32 minus 1 is 31. Yes, it is a prime. All right. Okay.
Hello.
Hello. Good morning. Morning. Okay. Morning. All right. I'm not going to take a long time today, but I'll just brief explanation about the proofs, and then I'll give you time to work on your assignment. Okay. Because today everyone should start working on assignment 2, B. A is everyone is done with the A, right?
Yeah.
Last question. Okay. And I see you both. So today everyone is going to start working with the assignment 2. And for that, I think we discussed yesterday about mathematical induction with different examples, like some of the squares of the natural numbers, sum of the natural numbers, and also with the fractions we discussed. So earlier we talked about the proposition. What is a proposition? Or a statement that is a sentence which is either true or false, but not the both. And then we talk about the quantifiers for all there exists, and also the connectives, that is if then and or if and only if, and we wrote the truth tables for all those conditional, disjunction, conjunction, and biconditional. And then when I was talking about the proofs, I gave you a brief explanation about direct proof and indirect proof. And then today there are more, there is an in-depth with the proof. So that is, I'm going to continue with that and then give you some more explanation about the 4 fundamental proof techniques, for including those. So there are 4 fundamental proof techniques. And that are: number 1, direct proof. Or you can say proof by construction, and this proof by contradiction. So this is, we call it as proof by construction. And second one is proof by contradiction. And the proof by induction. Number 4, that is proof by contrapositive. That means giving a counter example. By giving a counter example, we can prove also. And when we write the conditionals, we stated its converse, its inverse, and also the contrapositive. So something like, if the condition is if P then Q, if P then Q, its converse is if Q then P, and contrapositive if not Q then not P, and inverse if not P then not Q. So those are the conditions: converse, inverse, contrapositive. So under those 4 different examples, we discussed first 2 examples, and direct proof. In direct proof, there will be 2 steps. We can say assume P is true, demonstrate that Q must follow from P. That gives you the proof for first one. And each one has 2 different differentiations. Proof by mathematical induction. There are 2 to 3 different steps in each. Proof, in proof, direct proof, there are 2 steps. I'm going to give you different steps in these proofs, or different steps I can write, or examples I can say. In direct proof example, there are 2 steps to directly proving proving P implies Q. So the steps are, first step, assume that P is true. And the second step, demonstrate that Q must follow from P. Q must follow from P. And that's what we gave an example here when we look at the first example. So that's how the direct proof. So if X is even, then X square is even direct. So if this is my statement P, that's my statement Q. So this is P and this is Q. So P follows that Q. That's what they do. And in example, for the second one is proof by contradiction. We have three steps. Proof by contradiction. Proof by contradiction. Steps proving the theorem by contradiction. Theorem by contradiction. Step one, assume P is true. Second step, assume not Q is true. Not Q is true. And then demonstrate a contradiction. Proof by contradiction. And the third one is the mathematical induction, and we did a lot of examples yesterday. So I'm going to just write the steps today. What are those steps in proof by mathematical induction? To prove that the base case and then the inductive hypothesis. To demonstrate P implies Q by induction. We require that the truth of P and Q be expressed